Alright, so last time we had 12 people in class, and now we have like maybe 15 or 20. Those of you who are here may not realize this, but I actually gave the last lecture 3 times last Wednesday. First in class, then I tried to make it, then the sound didn't work in the recording, so I tried to re-record it in my office. And the first time I tried, it didn't work because I didn't press the button to start or something like that. So I had to give the lecture a 3rd time. So I know the last lecture really good, really well. Anyway, so let's get started. All right, we're going to talk about authentication today, which is like the second half of this security topic that we're covering. Okay, first, a few announcements. Project 3 obviously is due tomorrow. There were 10 test cases posted to Canvas. One of them was messed up the first time, and that's been fixed. And there's going to be homework 4 posted soon, so that'll be the kind of next thing to work on next. I don't think we have time for another project, I don't think. But it won't just be the next homework. You'll have, I think, another thing, like a 5th homework assignment that's like kind of a project, but not a full project. But we'll see. I haven't figured that out yet. Another thing is this Wednesday, the next lecture is going to be a guest lecture given by Julian Coe at NUIT, who's director of telecommunications here or something like that. So if you have questions about practical networking, bring those and you can ask him. And if you want to know, like in practice, if you actually want to build a campus network like Northwestern's, that's really quite sophisticated. What all goes into it. And so he's going to give a few slides in class. Then we're going to walk over to tech and look at some of the infrastructure there that supports the North Campus. Okay. Any questions? Okay. So let's review last lecture. We talked about 4 goals in security to try to, because this idea of security is like a kind of catch-all that means different things at different times. And even these words I'm giving to define it are kind of broad, but we can start to break it down into confidentiality, meaning that others can't see your messages. Reliability, meaning that your messages can get to their destination, they're not blocked from arriving. Integrity, meaning that when they arrive, they actually say what you said initially, they weren't changed. And authentication, meaning that the person, that you know who you're talking to. And then we're going to be talking about authentication in more detail today, because that's actually somehow the most tricky problem to solve in network security. And the reason we're so interested in security is because we have a lot of participants involved in your network exchanges. You have many routers along your path for packets to reach their destination. And that we can't necessarily trust those routers. We don't know who's running them. We also have different hosts on our local network that can potentially see our packets because we're using a shared medium of some kind. Even if we're using wired Ethernet, you can. There are times when packets go out to everyone because the switch doesn't know where a particular host is located, which of the ports. So to start solving these security problems, we talked about encryption, which is kind of the most obvious thing that comes to mind. I talked about some of the history of encryption, just kind of fun facts. But then when we got to the real important modern details, we introduced AES, the Advanced Encryption Standard, as the standard symmetric key encryption algorithm, meaning that this is used when 2 parties want to communicate. They each have some secret key, some secret random number that no one else has, and by using that, they can encrypt their messages such that you have to have that secret symmetric key in order to decrypt the message. Okay, so we call that shared key. We call that a shared session key, some key that both participants have that they need to communicate. And that works well. And in fact, AES is used in most encrypted internet traffic. But we have to somehow establish that shared session key initially, right? That's a big problem that's not easily solved. If you're contacting someone that you've never contacted before, you can't just send them the key over the internet because the internet's not secure. So the big solution to that problem involves public key cryptography. An example of that is the RSA algorithm or elliptic curve cryptography. These are 2 different algorithms, the traditional one and the more modern one that is used sometimes. And with public key cryptography, you have a pair of related keys. You have a public key and a private key that kind of fit together. They were generated together and they're mathematically related. And the public key is not a secret. It's actually shared to anyone who wants to talk to you. But it's used for encryption of messages. But those messages can only be decrypted with the private key that you keep secret, and that is related to the public key, but cannot be generated from the public key. You have to generate the private and public key from scratch together, I guess. And you just by seeing the public key, you can't in polynomial time discover what the private key was that went along with it, that's associated with it. That's the important thing. And RSA and ECC work in different ways. RSA uses modular exponentiation, ECC uses algebra on elliptic curves. But anyway, so that's the basic idea. So we can use these public key cryptography in order to share a symmetric key. So if I want to send you this random number I've generated that we're going to use as a session key, I can use your public key to encrypt it and then send that to you. So that allows you to establish shared session keys, but it doesn't solve, it still allows man-in-the-middle attacks to occur, which I'll review in the next slide. And we tried to solve this, we've started last lecture to solve this authentication problem. In other words, where we want to verify that a public key that is advertised to us actually belongs to the person we're trying to communicate with, and that we're not talking to some man in the middle who's actually going to see our traffic and then forward it on to the final destination. And digital signatures are the solution to that problem that also uses public-private keys. And I'll review that again today and talk about how they are used to establish transitive trust, which allows us to browse the web and visit new pages without and trust that they're secure without having ahead of time exchanged keys in any way. Okay. So we'll try to tie it all together today. Start off by reviewing the man-in-the-middle attack. This was the case when we had some router along the path that in the initial exchange, we were, these two parties are trying to communicate, and this one gives its public key. So remember, the public key I represent with a lock, and the private key I represent with a key, but they're just two different parts of the key, public key, private key. When the A shares its public key, the man in the middle actually replaces the public key with its own public key when it retransmits it to the final destination. So now that causes the other end of the connection to encrypt. Well, later on, actually, and then in the other direction, this receiver also sends its public key to the other side. But again, the man in the middle substitutes the advertised public key with its own public key. And at the end of this handshake, both sides are using the evil router's man in the middle public key here, the ones that are received on either side, instead of using the ones that are correct. So then subsequent messages can actually be decrypted by the man in the middle and then re-encrypted to the final destination without either party really knowing what's going on, because somehow they were tricked into using the wrong public keys. Right. That was the man. Anyone have a question about man-in-the-middle attacks? I hope that if you didn't make it to the lecture, you at least watched the videos, because if you didn't, then you're going to be a little bit behind on this one. But these next two slides are going to review the most important parts of the last lecture. Okay, so we tried to prevent these man-in-the-middle attacks using digital signatures. And I ended last lecture by explaining what a digital signature was, but then I didn't fully, I didn't actually finish up the discussion to say how those are actually used to establish trust and prevent man-in-the-middle attacks. Okay. But the basic idea was that a digital signature is a way to take a document, some chunk of data, and to attach an integer sequence to it, a bit sequence to it, a signature that can only be generated by someone who holds a private key. So what we do is we take the document. This has some claim, like, for example, google.com's public key is such and such. Right, that's a claim. And someone can sign that by taking that claim, hashing it to get a constant fixed size number, and then encrypting that hash. And then the only person using a private key that is only held by that one person. And they attach that signature, which remember is the encrypted version of the hash, to a document and distribute it along with a public key. And anyone who sees that document later on, so this is done by one person, the signer. This can be done by everyone who wants to verify it. They split it up into those three parts: the data, the signature, and the public key. And they basically try to reverse the process of the signature that was done before. So they take the signature and they use the public key to decrypt it, and that should get the hash of the document, because that's what was used as the input here. Right? and they take the document and hash it, because this hash function is well known. They can run the same one here. And if that hash of the document matches the decrypted version of the signature, then that means that the signature is valid. And they know that the person who generated that signature must have had the private key associated with that public key. And if they trust that if they know that that public key is valid for a certain person that they trust, then they can say that the claim was actually said by that person they trust, and therefore they should trust the claim.
I think you mentioned this in the lecture, but
yeah.
What function do you use to hash it? Is it standard?
It's probably like SHA-1 or MD5, one of the two. I don't remember. And there might be some flexibility in different certificate protocols, like specifications. Yeah. All right. So so far what we have with digital signatures is a way for statements to be signed by people who have private keys and public keys, and for those statements to be verified by others who just have the public keys. And if somehow we know that people have certain people have certain public keys and they're holding the private keys, then later on we can check. Those people can make sign all kinds of documents, distribute those all over the world, and later on others who knew what the public key was for that person can verify there's actually that person who generated those signatures, right? All right, so we can use this to provide trusted statements, and those trusted statements can provide transitive trust of new statements from people who don't know. Okay, so let's say we want to browse the web and visit thousands of websites over the lifetime of a computer. It's impractical to get a pre-shared key ahead of time from each of these thousands of websites. Like, we can't just hard code our browsers to know what the public key is for every different secure website on the internet. But what we do instead, but we still want to eventually determine what the public keys really are for those thousands of websites. The correct public keys are. We need the correct public keys, because otherwise some man in the middle will be able to trick us into sending our data to that man in the middle instead of to the actual endpoint. Okay. All right. So the way we solve this problem of finding the true public keys of all the different web servers, and I'm using web as an example, but this applies to any kind of network communication, is through the use of root authorities. Okay. So what we do is every computer that wants to communicate securely over the internet has to have a list of a few trusted public keys. And these are called root authorities. So my browser, for example, or it could be your operating system, or it could be your browser, or a combination of the two, has a list of some public keys that came installed on it from the beginning. And these are like public keys of root authorities that are trusted, and they're known to the developer of the browser or the developer of the operating system to be trusted, and somehow those were established and advertised. And so we have a few organizations that are root authorities that are in charge of then that we can trust statements from, basically. And if we trust a few people, then it means that those few people can make statements about others that we can trust. So, for example, those root authorities can sign certificates identifying another trustworthy certificate authority. Like, for example, if I trust, like Thoughty is one root authority that it goes back, is one of the earliest ones and most well known. If I know their public key and I trust them, and they tell me that, for example, Amazon has a certain public key, they can just write a document saying Amazon's public key is such and such, and they can sign that with their public key. Then when I see that in my browser, when Amazon provides that to me, even though I never contacted Thoughty, the actual root authority, Amazon can provide me a document when I visit their website that tells me what their public key should be, and that statement is signed by someone that I trust. And I know that someone else didn't forge that document, because they would have had to have the private key, Thoughty's private key, and Thoughty is one of my special root authorities that I trust is doing a good job of keeping their private key secret and not giving it to people to sign false statements. And they have some way of verifying the public keys are correct. So, for example, if I'm a website operator, if I start a new website, whatever, like ECS340.com, I want to allow HTTPS for secure connections to that website, I will have a public key on that web server that allows us to establish a session key. But in order for people to trust that public key, I have to generate a certificate signed by someone that most people trust, saying that, in fact, this new public key is the public key of ECS340.com, or whatever. So what I do is go to a certificate authority and go through some kind of process with them to give them my public key and allow them to verify that I, in fact, am the person who controls this domain, ECS340.com, so that when I claim that the public key for ECS340.com is what I say it is, they should actually believe me and they should sign that statement. Okay, so for example, they might email me, they might try to find the real email address of the administrator of that website and email it. They might look for a phone number for the organization and call that phone number and then ask me to repeat the public key and verify it that way. They might send me a letter to the mailing address of the organization. Those are different ways that a certificate authority can verify that the public key they've been given is actually the public key for a certain website, and they should in fact sign that statement that, saying that that's the public key. Because that signature later on can be used, will be trusted by others. Yes?
How does this relate to when you join a Wi-Fi network and there's a certificate involved in that process as well?
When you join a Wi-Fi network, I don't know exactly the detail. So certificates are used there in certain types of Wi-Fi networks, I think, to authenticate something about it. Yeah, I don't know the details of like that type of Wi-Fi authentication. So generally, you shouldn't have to ever, as a user, you shouldn't ever have to click anything that says approve. Like this, like here's a certificate, approve this. Like that generally is a sign that the person running the infrastructure is doing something wrong, because this all should work seamlessly. Like when you use your browser to visit a new website that was just opened yesterday, that works seamlessly. You get the little like green like lock on the upper left because the website's has done their work to generate a certificate that's signed by a universally trusted authority, a state that gives you the information you need to know to trust that that public key that's advertised is actually valid, right? So I think that when you're joining a Wi-Fi network, generally, just like with any other certificate situation, they should be able to provide you with a certificate that's signed by a trusted authority. And it may be a situation where you're joining a network where the administrator is too cheap to pay someone to sign their key. Because it's kind of expensive. It can be expensive to do these. Nowadays there are free options, but traditionally, because someone has to actually do some kind of real world, like meet space authentication of you, like actually like call you up or email you or like visit your organization. I'm sorry I used that word. That's yeah. That actually takes some effort, right? It can't be automated. There's actually a human usually involved in doing that verification, so it costs some money. All right. So on the web, you've kind of seen this before. Probably. Sorry. So if I go to Chrome and go to like Northwestern.edu, and specific, let's say I go to Canvas at Northwestern.edu, and the reason okay, so that redirected me to another site. But anyway, so right now I'm at whoops. So I'm at websso.it.northwestern.edu, and this is an HTTPS website, and that means it's encrypted, and there's a little lock here showing that the certificate verification passed. Okay, when I click this, I can get more information. Connection is secure. There's a valid certificate. If I click it, I get more info. It was issued by Incommon RSA Server CA. So CA stands for Certificate Authority. This is the name of some certificate authority. And the certificate has some details that, okay, the hash algorithm, in this case, is SHA-256. I think this is actually a parameter that can be changed for different types of certs. Issued at a certain time. It has an expiration date. So actually, this certificate will not be valid after 2020. It'll have to be some new one will have to be regenerated. And the subject here indicates that this is for a certain website, a certain domain, and that there's a certain public key. There's a 2048-bit number on the certificate, as well as a host name. So it's telling me this is the public key for this host name, and a bunch of other stuff. There's a certificate verification list. We'll talk about those later. But it's somewhere there's a signature. Anyway, so that was there's this certificate here that I was just showing you, but there are two other certificates involved in verifying this. So that certificate basically had one of Northwestern's host names listed, the public key for one of Northwestern's web servers was listed, and there was a signature from in-common RSA server, CA. And in order for us to trust that signature, we have to know in-common RSA server CA's public key. In order to know that's not one of the root certificates that's installed on most browsers or operating systems. It's one of thousands and thousands of different certificate authorities. In order for us to trust the certificate authority, we have to have like a chain of certificates that goes back to a root. So there's another certificate here that's included that is the certificate for in-common RSA server CA, which is signed by user trust secure. And user trust secure is the root the root authority. This is the certificate that was installed in either the browser or the operating system that I trust. So this web server actually presents all three of these, or maybe just two of them, to the browser when I connect. And because this root one matches one that I've already stored on my computer, I trust the whole chain. Okay. Any questions about that? All right, what's going on? That's that. Make sure this is still recording. All right. Okay, so to explain that more clearly, the public key infrastructure is the system that handles all this chain of trust, to create, distribute, and verify strangers' claims. And the particular claims we're most interested in is the public keys that are associated with different websites or other like host names or services that we might want to connect to and want to connect to securely. So this is a distributed and scalable way to verify public keys that simply requires the participants to have certain root certificates, some set of root certificates installed ahead of time that they trust, and then based on those root certificates, they start to trust other servers on the internet. Okay. So when the customer connects to shopping.com, www.shopping.com, we don't know ahead of time what the public key is of that server. So in order for us to learn what the public key is, the server provides us with a chain of certificates. So there is, first of all, its own certificate, which says that www.shopping.com has this public key, and that whole document is signed. So like this whatever is written here is hashed, and that hash is encrypted using the private key of, it's signed by WebbyCorp. WebbyCorp is something I made up, which is the intermediate certificate authority. So WebbyCorp has signed shopping.com's certificate, provides a signature, and the WebbyCorp's public key. This so far doesn't mean anything to us because we don't know who WebbyCorp is either. So we didn't know who shopping.com was. We don't know who WebbyCorp is either. We just know that someone called WebbyCorp is telling us that shopping.com's public key is this. But in addition to that, we get this intermediate certificate that was generated, that WebbyCorp paid for from a root authority. So we have among our root certificate authorities AAA Corporation, which I made up again, so we know what that public key is for AAA Corporation. And in this case, it so happens that AAA Corporation signed a certificate saying that WebbyCorp's public key is this. And that matches what's on the certificate for shopping.com that was signed by WebbyCorp. So essentially, AAA told us that not only is WebbyCorp's public key this, but WebbyCorp is a trusted certificate authority and should be trusted to sign other certificates. And if we trust AAA, then we should trust WebbyCorp. And if we trust WebbyCorp, we should trust that shopping.com has this public key. Simple, right? It is kind of simple once you get it, but it's a chain of trust, and every step in the chain is established through digital signatures using that picture I showed you before. Okay. So any questions about that?
You have to verify using that process of hashing.
Yeah.
Comparing.
So the browser will do that. Yep. Every time you visit a web page, if it's the first time you're going to that web page, that the server will provide you with a chain of certificates, and then you have to like follow the verification process to like decrypt the signature using the public key. So verify that, and then hash the document, see if that matches. But then also take that, then determine whether or not you trust who signed it, and if not, do the same process on the certificate provided that's supposed to tell you to trust that authority, right? And eventually, you need to make sure that it maps to some root that you trust ahead of time.
How do you trust all of the root certificates? How do you?
Well, that's a good question. Someone told you this is an unsolved problem so far. So far, all we know is that. So in practice, these are you might have like I'm gonna actually have a slide that covers this later. So let's just delay that until I have a picture that explains it better. Okay, so in order to get one of these certificates, like I kind of answered, started to answer when answering a student's question. Like if you're setting up a new web server and you want people to use HTTPS, you generally have to pay a fee to a certificate authority and send them a certificate signing request. So this is the document that you want them to sign. So for example, the certificate signing request, the CSR might have this common name, Northwestern.edu, public key, this. So this common name just means basically like what the domain is of the website. So, and you can imagine this is some website, your own website that you're trying to get a key certificate for to set up a web server. You give your host name and your public key, and you say, okay, this is like what I want to use, right? Can you please sign this so that others will trust that this is correct? And the certificate authority, on receiving the certificate signing request, has to somehow verify this claim. So, because it could be anyone that just I could go back to my office and generate okay, google.com, public key, whatever. Okay, I'm Google. Yeah, sign this. That's not good enough, right? Someone has to verify that if we're getting a request for google.com, it's actually coming from google.com. Someone trusted at google.com. So they had to do some verification, and that's what you're paying them money for. For example, they could look in the Who Is database, which we didn't really talk too much about, but this is part of the domain system where you can figure out who the administrator is for a certain domain. It's like a public database. So there's an email address listed there. You could just email that person and say, hey, we got a request for a certain public key on one of your domains. Is this correct? And then they could answer. That's kind of a weak way of doing it. You could look up a phone number in some trusted source, like a printed telephone book that you think is trustworthy. You call up the company and ask for someone, and eventually figure out okay, this person requests public key. Is this the right public key? Send a letter. You could visit the office of that organization and actually ask them. You probably wouldn't do that. You probably wouldn't do this. But anyway, you have to verify the public keys. You have to verify the certificate signing request somehow using some information that you trust that would hopefully, whatever they do is sufficient to prevent random people from claiming to be the organization that an organization that they're not, and therefore to get something signed that shouldn't have been signed. Okay. So once the certificate authority is satisfied that request came from a legitimate source and it should be signed, it will compute the digital signature using its private key and then add that digital signature to the CSR to create a certificate. So basically, it'll compute some number that no one else can compute except itself, because it's the only one that holds the private key, and share that number with the world. And just by sharing that number, it has verified this. It's certified that statement. Okay. Yes.
So can a website be HTTPS before it's certified?
It can be, but every time a browser visits it, it'll get a pop-up saying this is like not private. Like, do you really want to go here? That's what happens. Like you said, you probably run into that on. Well, okay, if you, well, I hope. Well, it's great if you haven't, but I know I have. At least if you're like developing your own website, often in the early stages, like if you haven't gotten to that stage yet, you'll have to do a lot of clicking through to say like, okay, go, like, really do connect to it, even though it's not giving me a valid certificate. And that means it's basically the browser is telling you that you're liable to be, you're vulnerable to a man-in-the-middle attack because we haven't verified this public key. It looks like something funny is going on, and it could be that you're just on a development machine that doesn't have the right certificate, or it could be that something really is going on. Okay, so about root certificates, like you were asking about. So at macOS last spring when I did this, so it came with 170 root certificates, actually quite a lot, more than I expected. So it's a lot of root certificates that just came installed in the OS, basically. So, and here they are, right? So from AAA certificate services to, I mean, Amazon itself is root certificate authority, and others. Okay. So, and notice that these have an expiration date, but the expiration dates could be quite long out, like 2040. One of these expires. That's like a long time, right? In computer years. So, and each one of these includes a public key in addition to the name of the service and an expiration date. And so basically what happened was, the way that these were generated was that some engineer at Apple or a group of engineers decided to include these. Like someone decided to install these in the Mac OS standard distribution, and so they have a security team that somehow verified that each one of these is correct. And because these are root level certificates, it's very important that they are correct, because if any of them was wrong, it would break the whole internet security on that operating system. So basically, I'm sure that in this case, Apple for Mac OS did something to verify. They contacted each one of these organizations manually and figured out, okay, what's the public key you're using? Like, how do I know that I'm talking to someone who actually works there? And let me double check by talking to someone else who works there, and so on, right? Is this really your public key? We trust that someone at Apple did that for all 170 of these, and that list was safely included in the source code for the Mac OS that generates this, and it wasn't tampered along the way. And that's how it ends up on all Macs. And the same thing happens for your smartphones and Windows and Linux, and different browsers have different. Sometimes will not use the operating system list of certificates, but their own list. So, for example, the Chrome browser source code might have a list of certificates that are trusted as roots somewhere in the source code, and whoever is responsible for that source code and responsible for the security of that browser has to verify that those are correct. Okay, so it's a manual process for these root certificates. And then you also have to, as a user, you have to make sure that this list is not tampered with after your OS is set up. Because actually, as a user, you can delete these and add new ones. And that's something a user can do that can cause like a dramatic security vulnerability without really knowing it. Because this idea of root certificates is not very clear to most users, obviously. Okay. Questions about that? Root certificates? All right, so here's the details of a root certificate, just one of these. I mentioned Tarzia before. It's been around for a long time. And in this certificate, so this is the document that is signed. All certificates look like this with the same kinds of components. You have an expiration date here. The subject's name is a combination of like the organization and like other fields and the country and stuff. And this certificate was actually issued by a different organization that the issuer here is the person who signed the certificate. In this case, since it's a root certificate, there's no chain. It's just a statement that's signed, that's self-signed. So actually, this is the same as this. And so the public key being advertised is signed using the same public key. Because it's a self-issued and self-signed certificate. So actually, for this one, you don't necessarily need to verify that the signature is correct because you're trusting it to begin with. Yeah, so you have to have some kind of outside reason the trust that this certificate is actually valid. You can't use the any public key to verify it. But then an intermediate certificate, so this is an example. So here I had Thought primary root CA. Now this is Thought SHA-256 SSL CA, which is the same company, but it's a different certificate used by that company. This is an intermediate certificate that it uses to sign like customers' certificates. And it has the same basic parts up top, but then the issuer is different, and the signature down here is signed by that root authority I showed before. So overall, the summary of this certificate is that the Thought SHA-256 SSL CA has a certain public key listed somewhere here, I guess, and it's signed by the signature here, signed by I think this issuer. Thought primary root CA signed it and generated this signature. And yeah, so I just showed you this before, but like in your browser, you can see the chain of trust for any website by different browsers have different UIs, but basically you normally click the little icon next to the URL. Okay. And yeah, there's a chain. This is just an example of a chain of trust. I think we already did an example with the before, but you can go through this later if you need to. So those are the basics of public key infrastructure and chains of certificates. Now, I mentioned that root certificates are kind of hard-coded from the start by the developer, or some developers, and but users can actually add and remove root certificates if they wish to, which allows, which controls which organizations and public keys are trusted to vouch for others. So you can actually control, if you can look at that list and say, okay, yeah, maybe Apple trusted these 170 people, but I don't trust all of them. I only trust 150 of them. So I'm going to remove these 20. Or like, I don't like the names of these 5. I'm going to remove them. Or like, I don't like these 100. Whatever. You could like do that. But what would happen if you went through and removed lots of these root certificates from your OS? This is a question for you now to think about. Any ideas? If you decided to go to your OS and remove like half of the root certificates. Some things would work, some wouldn't. Yeah, what do you think?
Well, I mean, anything that's signed by those roots would then be invalid, right?
Yeah, so what kinds of things would be signed by those roots?
The intermediate.
Yeah, but which intermediates? Like, we don't know, actually, right? So like some fraction of websites that you visit would stop working. So you'd visit, like some websites would work fine. Others would give you some kind of warning saying like, oh, like this isn't trusted, are you sure you want to proceed? Others would work partially, but then like some of the images would be broken because images were sourced from a domain that has a certificate that was signed by someone that you no longer trust, that kind of thing, right? So some kind of weird behavior. So generally you wouldn't do this, because like the list of standard root certificates is kind of stable and accepted by most people around the world. Like it's a certain list. If you suddenly if your operating system has a reduced list smaller than that 170, then your users are going to complain like, oh, I can't visit certain websites. But there's a little bit of back and forth, because then website operators might say, oh, I'm not going to buy a certificate from you because your root certificate is only in 90% of computers' databases, not all 100%, like not 99% like this other one. There's a little bit of like salesmanship that happens in the certificate business, where some certificates are more expensive than others because they're supposedly trusted by more machines out there, because the company has better security practices, basically.
Do machines have their own certificates as well?
Yeah, sometimes. It depends on it. So I'm thinking of actually that's a good question, and I'm going to have a homework question about it, but because it gets you thinking. But so often we think of certificates for authenticating servers, because because the server has a clear identity. Like there's a host name. When you go to a website, you go to like gmail.com. You know that word ahead of time. You just type in, or that host name. You type in that host name and you go to it. Whereas for individual computers, what does it mean for? It's less clear what it would mean to verify the identity of a computer that's owned by like an individual person. Like, because people generally are not trying to contact you, and they're trying to verify that you're you versus someone else. I mean, they could be. Like, for example, one case where this is used is like encrypted email, like GPG mail, where if you want your email to be encrypted and for others to trust that it's actually signed by, that you're the one who signed it, and also to be able to decrypt it, you have to have some way to distribute a public key for yourself. Okay. And without necessarily contacting everyone ahead of time, you could have a chain of trust for public keys for email addresses. In that case, the email address would be like the identifier. But generally, for this to work, there has to be something that you're verifying. So for the case of what we've been talking about so far is like host names and public keys. Like, is this the right public key for this host name? The example I just gave was like email addresses. Is this the right public key for this email address? So you have to have some notion of identity that can be summarized in a string or some kind of digital document that is verifiable. But in practice, the way that most users are authenticated is with passwords, which is different. Okay, so that was one question about root certs. On the flip side, what would happen if you added a bad root certificate? So if you just willy-nilly added random root certificates to your computer, what would happen? What could happen?
You might access a website that you think you know that website's identity, but you're really accessing some other.
Yeah, right. So you think you're accessing Citibank.com, but actually you're accessing some other organization that's not Citibank.com. You put in your bank password and they get it, right? So for example, it could be a man-in-the-middle attack where like one of the routers is impersonating you, or some other machine that has like poisoned DNS to get you to go to a different IP address instead of the correct IP address for that service. Yeah. All right, so let's look at the man-in-the-middle attack again, and this time we're going to show how it's foiled or blocked by this public key infrastructure and by certificates. Okay, so we still have client A connecting to server G. Gadgets.com. That's what it is. So A sends out its public key. The man in the middle rewrites it to a different public key. Gadgets.com doesn't actually care because Gadgets.com doesn't have a way of authenticating a client, like you were saying. Like that doesn't exist in this server-to-client direction. Okay. But Gadgets.com advertises its public key, G. It also adds a signed certificate. That's this little paper thing, sub G. And this goes back to the man in the middle. Now, the man in the middle doesn't want to relay this public key. It wants to give its own public key. So it changes the public key, and it attaches a different certificate. It can't include this certificate because this certificate says the public key is this public key. It has to give a different certificate. So it generates a different one. It turns out that the man in the middle is not going to be able to generate a valid certificate in the response. So it's going to have one of several problems. Problem A, the domain name of the certificate might not be gadgets.com. It can't be gadgets.com because there's not. We'd imagine there's not a any valid certificate signing authority should not sign a certificate from this random person claiming that they're gadgets.com, because when they try to verify it, that should fail. Okay. Or it might list gadgets.com, but the signature might be invalid because it was signed with some random public key that the man in the middle generated. Or it could have been signed validly by some issuer that's sketchy and untrusted. So for example, the man in the middle could have his own certificate signing authority, its own public key, and it could sign whatever it wants with that. But that's not, that public key that was used for the signing is not something that's trusted by the client or trusted by someone that the client trusts through a chain. Okay? So this certificate's going to be invalid for one of three reasons. This is going to be passed back to the client, and the client, if it's implemented correctly, will check this certificate and notice that one of these three problems exists. And you'll see the certificate's fake, or maybe the certificate's missing, but in either case, the client should stop the connection. Should drop the connection, right? That makes sense? Now notice that the server doesn't notice any attack is happening, because the server is not expecting a signed certificate from the client. Because this work of getting a certificate in order to have secure communication, that involves work. It involves like potentially paying for some kind of verification. So all the clients don't go through that process. It's just the servers. So generally, to authenticate the client, we use application layer mechanisms like passwords. So if we want to make sure that the person who's connecting to gadgets.com and asking to see a shopping cart or an order history is actually the person they think that made that order initially, the application is designed to ask for a password that was entered before, and that's not a network level authentication. That's application layer authentication. Does that make sense? Okay. So we can actually foil this and allow man-in-the-middle attacks if we include some sketchy root certificates on your machines. So this actually happens sometimes. So some corporate or campus networks might require the machines to install a new root certificate when connecting network services. And I'm not sure if this is what a student was asking about before, but it could. So this is maybe related to what you're asking about. It depends on the specific scenario you're thinking of. But sometimes in order to connect to a network, you have to install a new root certificate. And by doing so, you're actually exposing yourself to you're exposing your traffic. So for example, so often what is going on is that the network operator has some kind of appliance that's monitoring all your traffic and supposedly scanning for like doing security, like helpful security things, like making sure you're not visiting certain websites or whatever. But this is actually a pretty intrusive thing to do, and probably shouldn't be allowed. So if you're asked to install a new root certificate, you should do that, even if the instructions from your helpful IT staff tell you to do that. Because I've seen that before. And there are also some legitimate debugging tools which would ask you to install a new root certificate. This is legitimate because, like, for example, if you're developing an HTTPS application, like an application that communicates with a server in an encrypted manner, but you still want to debug the network traffic to see what's being sent back and forth between those two machines. If it's over HTTPS, you can't use Wireshark to see the traffic because it's encrypted at the application layer or at the above the transport layer. So there's a program called Charles Proxy, which does that. It installs a root certificate, and then it acts as a man in the middle to transmit traffic. eBay? Oh no, it's supposed to be, yeah. Right. But by doing that, you're trusting that the developers of the Charles Proxy software have developed the software carefully enough that, for example, a random new root certificate is generated for each installation, and it's not shared back to their own servers and used to exploit your traffic. So you'd probably want to look at the source code if you really wanted to be safe. Okay. So if we had a client that actually installed a new root certificate, in this case I'm calling it the Big Brother public key sub B, we can have a successful man-in-the-middle attack, right? Because this root certificate that was added to this computer, this is not one of the standard root certificates, it's a new one. It's going to be used to snoop on the traffic from this user. That public key and private key pair are known to the attacker, which in this case is a router in between. And now when the router in the middle tries to do the man-in-the-middle attack, it can, so when gadgets.com provides its public key and certificate, which is signed by a legitimate authority, the man-in-the-middle gets that, and the man-in-the-middle can actually generate a new certificate for gadgets.com, which it can sign using its own private key, which corresponds to a public key that's trusted as a root by the client. So the client will end up trusting the certificate that says that the public key for gadgets.com is this public key M that the man in the middle has. Okay. So the client will accept the connection, and because this new root certificate authority, root certificate has been added to the client. Right. And in this case, the public key infrastructure failed because the client installed the root certificate from a malicious party, and this, this shouldn't have been installed because this root certificate, this party is willing to sign fake certificates, in particular for this router that wants to impersonate everyone. Okay. Cool. All right, so that so far should be enough to solve the man-in-the-middle attack scenario that we've been worrying about. All right. So there's one other detail, I guess, in this public key infrastructure. So far we've said that private keys are supposed to be kept private, and the security of the system relies on that. But these are systems with humans involved, and humans make mistakes. And in particular, sometimes private keys get shared. Like it could be someone breaks into a server, steals a server. It could be someone accidentally copies it to their laptop, and then the laptop gets hacked, or they accidentally write it down in paper and someone takes the paper, or whatever. There's like a million different ways that a private key could get leaked. And we have this whole big system where like internet security depends on like 170 private numbers being kept private. Like that's kind of ridiculous when you think about it. So there has to be a mechanism built in to react to deal with the situation inevitably when one of those 170 numbers gets leaked, because the stakes are high and eventually it'll happen, and people make dumb mistakes sometimes. And it's not just those root authorities, private keys that need to be protected, although those are the most important ones to protect, but we have thousands, millions of web servers, and each one of those millions of web servers has public and private keys, and the private keys on those web servers also have to be kept secure to prevent others from impersonating that each of those individual web servers. And obviously, not every web server is secure, and not every employee that leaves an organization gives up all the credentials that they should. So for all these reasons, like you have to have a way to deal with losing control of your private key. Even though you have a certificate that was signed by an authority, and there's an expiration date of, let's say, 2022 that says until 2022, this public key is the correct one for Google.com, but then suddenly a Google employee leaves with a private key. You don't know where they went. And we have all these browsers that are going to trust that private key for the next 4 years, right? You have to have some way to revoke this trust. So the way this is done is with certificate revocation lists, CRLs. So basically every certificate on it has a URL that tells you where you can go to check to see whether it's still valid. So there's an expiration date on the certificate, and that's useful, but there's also a place where you can go and check, just in case the certificate was revoked. So a client may check this. A client may consult the certificate revocation list before trusting a certificate, but it's slow, actually, and it usually doesn't do this, because that creates like a centralized bottleneck in this whole trust process. Like originally, the beauty of this system, and we didn't really talk about it. But maybe I'll have a slide next year. But the beauty of the system is it's totally decentralized and scalable. Like when I want to verify the public key for a new website that I visit, I only have to communicate with that website, because that website has a document it can give me itself that somehow, like almost magically, allows me to trust that the information that is written on that document, right? The public key of that server, right? I don't have to go back to ask anyone else. Oh, is this really the public key for that person? Because they on their own went to that third party and got a signature from that third party that they can show to me, and I can trust that signature without having to go back to that root authority and ask it. So it's a totally distributed system, really scalable. It's a great design, but once you start losing private keys and revoking certificates, it all falls apart. The scalability aspect of it falls apart, because we have these certificates that have expiration dates many years in the future, whereas in reality we may wish to expire those sooner if there's a leak of a private key, like a security breach, right? So this is a big problem with public key infrastructure, which is not really solved, I think, at the current time. So clients can check CRLs. They should do it occasionally for important sites or sites that you're visiting frequently, I guess, but I don't think it would be a good rule to just say always check the certificate revocation list whenever you get a certificate, because that creates a centralized bottleneck in for all the visitors visiting a certain web page. Basically, we'll first have to check this other source to get the public key. Yeah. Okay, so an example of this kind of I guess leak was in 2011. Famously, Komodo was hacked. Komodo, although it has a ridiculous name, was a trusted root authority, and so they were one of the root authorities, and their certificate signing server was hacked. In this case, it wasn't exactly that their private key was released, but they had a server that had like a username, password, login kind of system that allowed trusted affiliates to request digital signatures using a username and password. And I think they had some kind of dumb like default username and password for it. Like, so this is like an internet security, like one of the most fundamentally trusted internet security companies out there that like made a really bonehead error in their system in terms of not having strong passwords and not changing the passwords and all that. So anyway, so the attacker was able to generate whatever new certificates they wanted to because they knew this username and password to connect to this system. They weren't really a trusted affiliate, but they were pretending to be a trusted affiliate. And the trusted affiliates were like the intermediate signers that worked with that were signed and determined by the root authority. So basically, you could get whatever new certificates you wanted, like generate Gmail, Yahoo Mail, and Hotmail certificates, and then try to intercept direct users to your fake versions of those pages to get their passwords. And once you have someone's email address or email password, you can get all their other passwords by just doing password reset, right? So so in this case, what happened was that these bogus certificates that were generated were revoked, but then also the root certificate was like basically Komodo became a really like a mistrusted name in internet security, and the root certificate was dropped in some browsers so in the future, right? And actually, I'm not sure how many browsers did drop the root certificate, but if they did, you can imagine that would have had a huge impact on internet security, because basically you had thousands of websites whose certificates were purchased in the past and signed transitively by Komodo. Suddenly, if the browser is no longer, just like the example I gave before, what would happen if you deleted some root certificates? That's essentially what potentially happened, because this company just lost trust in the marketplace, right? And suddenly all these other websites that had done business in the past with Komodo to get their certificates, those certificates no longer be valid because the root was no longer trusted. Yes?
So if you're one of those big services, can you register with multiple certificates so that you can send multiple? And I mean, if one needs to be revoked for security reasons, you still have 3 others that are valid?
Well, you can have, generally what happens is you have one root certificate, and then you have several certificate signing authorities of your own, like underneath that, and then those ones can be revoked. But then the central one isn't, because you can't really. I don't think the root certificates are ever checked. Like those are like hard coded and they don't change. They can't change really, because you can't go anywhere to check. To even go to a website to check our certificate revocation list, you have to have public key infrastructure working, because like to make a secure connection to that server to download the certificate revocation list, you need something to trust to begin with. Yeah. All right, so let's talk a little more about hashing, because this applies both to digital signatures but also to another scheme called message authentication codes. So remember, with digital signatures, this was the process, right? We hashed the data, and then we encrypted the hash to get a signature. This hash here is quite important, because we're encrypting the hash, but hashes are not hashes can expose some vulnerabilities, basically. So The reason we hash, remember, is that the RSA encryption algorithm we use here has to operate on a plain text here that's either 1024 or 2048 bits. So let's say it's 2048 bits. So it has to be, it can only be that size. It can't be larger. It can't be smaller. But when we generate the signature, we're actually signing not just this one document, but we're signing every document that maps to that same hash value. And there's an infinite set of documents that maps to the same hash value, theoretically. So we have to be confident that all the other documents that correspond to that hash are random and can't be used by attackers to make claims that would be harmful. Right? So let's give an example. So if the hash is 256 bits, then it can take 2 to the 256 power of different values, so lots of different values. But certificates are longer than 256 bits. So let's say certificates are about 2,000 bits long. That means that there are 2 to the 2,000 different possibilities of documents that long, right? If we divide the two, we get a huge number of expected documents that share each hash value, right? So, and if we let the length of these documents to grow to arbitrary size, you can get an infinite number. That's why I say there's an infinite number of documents that you're signing. So, for example, if we had this certificate for gadgets.com that says a certain public key, that lists a certain public key, and other information like the country of the organization, whatever else was listed there. We hash that to get a number, and then we sign this number, right? In doing so, we're actually signing a bunch of other documents. So, for example, we have this other certificate that lists this weird random name, this public key, and this also, by chance, hashes to the same number. And so any signature for this one will also be a signature for that one. And there's, by virtue of this simple mathematical argument, there are many, many different documents that correspond to that same document that we signed, including this other one. But all the other, we hope that all the other valid, useful certificates like shop.com with this public key hash to different numbers, so that the signature for this one can't be used to verify, for example, this other one, right? So basically, we need a hash function that's good, that will ensure that these documents here are random and not useful documents. So when we sign something, even though we're signing an infinite number of claims, we're only signing one claim that can be found in a polynomial time that has any meaning that would not potentially be used to harm us in some way. Okay. So we want to use a cryptographic hash function, not just any hash function. So cryptographic hash function, I'm just using the notation capital H as a function, is one that makes it computationally infeasible to do two things. First of all, map backwards from the hash output to input. So for example, if we hash x to get some value, we shouldn't be able to use the hash of x to go back to x. And then secondly, it's computationally infeasible to find two inputs that map to the same hash value. Or more strongly, to find, given a certain hash and an input, to find a second one that hashes to the same thing. Right? Even though we know that there's an infinite set of these XY pairs that hash the same number, because the hash space is smaller than the actual data space we're dealing with, the input space. The output space is smaller than the input space. We have to design a hash function to make it nearly impossible to find these pairs of values that map to the same number, and also to map backwards from the output to input. Yeah. So similar to a good symmetric encryption algorithm, you need good confusion and diffusion for the function to behave essentially randomly, and for different bits to be affected by different, and the output to be different bits in the output to be affected by different bits in the input in sort of a random manner. Right. So examples of good cryptographic hash functions that are used for both signing and message authentication codes and lots of other things are SHA-1 and MD5. And So that's what we use, right? And so terminology here, sometimes we talk about, if we have a message that we're hashing, sometimes we call it hash of the message digest. So digest is a word that often means hash. Okay. And so let's see how we use those and why it's important to have a strong cryptographic hash function. So with digital signatures, if you sign a SHA-1 hash of a document, so a cryptographically strong hash, then and we publish that signature, it will be difficult for an attacker to construct a second document with the same SHA-1 hash as the original document, and for them to use my signature basically to verify some other claim. It'll be hard for them to find some other claim that maps to the same, that corresponds to the same signature. By contrast, if I used a dumb hash function, like a non-secure, non-cryptographically secure hash function, problems could arise. Like I could sum up all the bytes of the document to get a hash, like a byte-sized hash. This would be bad, and forgery would be really easy. I mean, this is an extreme example to show like, but there are middle cases that are like not so trivial to fool, but with some effort you can find two documents that map to the same hash. So for example, this dumb hash function that sums up all the bytes, if you apply that to the statement fun and cats, that hash is the same as the hash for gun and bats. Okay, because what I did was I took the letter F and I moved it up one, and I took the letter C and I moved it down one. So those two changes cancel each other, right? So if I signed the statement the hash of the statement fun and cats using this dumb hash function, that same signature would be valid for the different statement gun and bats. And I could, with this dumb hash function, I could easily construct all these other statements that were equivalent to the thing I signed, but were not really what I said. Right, so this using a bad hash function, even though I used a good public key encryption scheme, and I was using a chain of trust and whatever, like if I use a bad hash function, all of it falls apart because I can make claims different than what were originally signed by like kind of reverse engineering the hash. Okay, so any questions about that, by the way? I think this is, well, almost the last thing. Not quite. So another place where we use hashes for network security is with message authentication codes. So here's a case where unfortunately we're using the acronym MAC again. It's a different MAC, message authentication codes. So this is a case where we want to authenticate, we want authentication and integrity, but not confidentiality. So we don't want to encrypt the message. We want to allow everyone to see a message, but we want the receivers to know that it came from us and it wasn't changed. So we want others to be able to verify, okay, this is a statement by me, and I can trust that it was from me, but anyone can read it. So, certificates, digital signatures are one solution to this problem, but a simpler solution is message authentication codes that applies to some situations, not every situation. Okay, so this is, now we're moving on to something that has nothing to do with like web browsers and HTTPS. This is different. This is used for certain other simpler network protocols. Okay, so what we do with a message authentication code is assume the sender and receiver both have a shared secret, similar to what we did with the AES symmetric key encryption. We each have some random number that we arrived at somehow. And we could have used public key cryptography to assign that session key or share it. And we compute a message authentication code by taking the message and adding the key to it, and then hashing that. So we take this message that is actually not secret, we share it with everyone, but we add to it some random number that only we know, and then we hash it. And then we send the message along with the MAC, the message authentication code, to the world publicly. So we can broadcast this to everyone. Everyone can see the message. Everyone can see this weird number we computed. But the receiver, if the receiver has the same shared key, they can do the same process of calculating the MAC for themselves. So they can take the message and add the key to it and then hash it. This is just a well-known hash function. And they can verify that the received MAC is the correct one. But crucially, no one else could have generated that unless they had the shared secret key. Okay. And by revealing this MAC itself doesn't reveal anything about the private key because the hash function is cryptographically secure. It's a cryptographic hash. It can't be reversed. So this is kind of an alternative. This is a type of symmetric key exchange similar to AES, but this is actually faster than AES. AES is slower than the SHA-1 hash. So this could be more efficient than using symmetric key encryption, but really the reason you would use this is for some situations where you actually want third parties to see your messages. You want messages to be public, but you also want a certain pair of people or group of people to have a shared key to also be able to verify that whoever created the message was actually like one of the trusted people that has this shared key. Yes?
Can you give a concrete example of that?
Okay, so let's say that I want to give homework assignments to the class, and the TAs and I all have a shared key. I want all the students to see the homework assignment, but I don't have time to meet every student ahead of time to give them some kind of shared key or whatever. I meet the TAs and we exchange a private key. We agree that the password is going to be network's great, right? That's the password. So everyone can see the assignment, but then the special group of people who all know the passwords networks are great can verify by taking that message, which is a homework assignment, adding to it that key networking is great, and hashing the whole thing. We can generate a MAC, message authentication code. So if an assignment goes out and it has a MAC attached to it, all the students can see the assignment. They don't know whether it's a true assignment. They have to decide whether it's worth the risk of not doing the assignment because they think it's fake. But all the TAs can actually verify that this is actually an assignment that was released by one of the teaching staff, because when they see the MAC, they can take the assignment and add to it. Networking's great, computer hash, and see whether it matches. I mean, that wasn't a really. Was it? First of all, does that make sense?
Yes, but I have another question.
It's not a really good concrete example because it's not like a real networking example, right? But yeah, go ahead.
Then how do you know that? Well, compute the MAC to verify the received MAC. How do you know that the MAC computed is actually correct?
Because you use the secret key to compute it. So the message you received was a combination of the message itself plus the MAC, right? So you use this to verify that. You use the MAC to verify the message, and you recompute the MAC by taking the message, adding the secret key to it, and hashing it. Yeah. Okay. It would be good to have some. So this is used, I think, in some networking protocols where you have advertisements of routes and things like that, and for different routers to trust what's being said by the other routers. I think that MACs are used for that purpose. This is a case where in general, it would be nice to authenticate every message, but not everyone has the information they need to authenticate every message. So if you have an optional authentication that happens if one of the if the receiver happens to be one that has gotten a copy of the shared key, but if you haven't gotten a copy of the shared key, you can still use the information that was provided. If it could be a BGP route, for example, it's advertised. You could just trust the BGP route because you haven't received a shared key. But if you happen to have previously had a secure exchange with the advertiser to get a shared key, then you would be able to both get the message and verify that it was from the right party. That's maybe a kind of example. Okay, this should not be spinning. So, how does this work in practice? In actual web traffic, we use what's called transport layer security, or TLS, to implement encryption and authentication inside of HTTP, or not just HTTP, but all kinds of network communication, network connections. So TLS is actually kind of a layer between TCP and an application layer. Usually the application layer we're talking about is HTTP, and then when you add HTTP and TLS, you get HTTPS, okay? But TLS kind of, it uses it's built on top of a TCP socket, and it does public key encryption, including things like doing the initial handshake with public keys and then switching to a session key with symmetric key encryption, and then also the library you're using for TLS will also do the PKI, like chain of trust verification, whatever. That's part of the software implementation, not the network implementation, though. Okay, so you now have a packet that has all these headers from before, in addition to a TLS record, which is a type of header, plus inside of that an encrypted body, which probably has some chunk of an HTTP response. And because TCP provides a stream, like a streaming connection, not a series of packets, this isn't really a header because it might not be at the beginning of a packet. It's just these record headers are interspersed in various places throughout the TCP stream. And then after the TLS record, you have some encrypted data, then you have later on you have another TLS record, and so on, right? So what happens when you make a secure connection, you first have a TCP handshake. Remember our old friends, SYN, SYNAC, and ACK? Okay, seemed like a long time ago. Sequence numbers, remember that? Yeah, okay, great. So you have that three-way handshake. I guess you send back the ACK this way. But then along with the third part of the handshake, you start a TLS handshake, which is also a three-way handshake, where you have a client hello, which is like the initial thing, which is kind of like a SYN. So in this first stage, both ends have to establish which ciphers they're going to use, like which version of RSA, for example, which version of AES, if any, or you can use ECC instead of RSA. Basically, they have to choose what cryptography they're going to use exactly, because there are a lot of different options, because the different ciphers have evolved over the past 20, 25 years that this has been used, 30 years. So each side has to discover what capabilities they have, which is more complex than with TCP. TCP handshake was mostly just about setting initial sequence numbers. We didn't talk about it, but there were also some parameters that were exchanged here. Like there are some differences in different TCP connections that you can set, but for the most part, it was just sequence numbers. But here, you choose your ciphers, you exchange keys, and then you start exchanging data. Okay. So it takes longer to establish this encrypted connection because you have one handshake and another handshake before it can start. Okay, but you can't start this TLS stuff until you have a TCP stream to deal with. You can't have a TCP stream until you exchange sequence numbers. Okay, so does that make sense? I didn't talk yet about what it really does here, but for example, it does things. So it has to establish different keys. There are actually 4 different keys used. So both their sender has an encryption key and a MAC key. So actually, message authentication codes are used in TLS. And also the receiver has another pair of those, different ones, and so on. Okay. So I'm not going to talk too much about TLS because it's complicated. I think understanding the theory, how the public key infrastructure works is useful. But there are a couple of attacks I'm going to mention that should help you to understand why TLS is hard to get right, I guess. So first of all, we might have a packet replay attack. So even if encryption works, where we have a packet that we can encrypt a packet so that only the receiver can see it, you might have a packet replay. If you resend the same packet twice, like if a man in the middle sees a packet transferring between 2 machines and just makes a copy and sends it again later, that could cause a problem, right? Because it could cause the same data to be received twice. And it didn't have to know the key to do that, right? So to prevent packet replay attacks, TLS includes sequence numbers different than TCP sequence numbers. These are like TLS sequence numbers, so that if a packet can only be seen once, right? That's a fairly straightforward solution. Another kind of attack is an entire connection replay. So an attacker might observe the entire client-server interaction and replay it. So the TCP handshake, the TLS handshake, all that stuff, right? So for example, I'm on a web page and I buy a product and there's a web request that happens securely. Like I submit my credit card and whatever, the order information. If an attacker sees all that traffic, they could replay it later to have me buy the same thing again and again and again, right? Theoretically. I mean, it depends on, I'm simplifying it because usually that wouldn't be in one request. Well, let's say it was in one request, right? You don't want that to be allowed. You don't want an entire connection. And again, this attacker has no idea what private keys are being used. They just observe what's on the traffic on the network and replay it. So a solution to this problem is for the receiver and sender to send a random nonce, which is like a random number, in the handshake. And the person receiving that nonce has to include an encrypted version of that nonce in the response. So basically what happens is every client-server interaction is forced to be different because just because I observed the last interaction between client and server, the next time around it will never play out the same way because the server and the client will both generate different random numbers in the second step of the handshake. So yeah, so like even if I'm sending the same request to the server here, if it, like in this step here, let's say, that the request, I can't send the same exact packet back because the nonce that came in here, that random number that came in here will be slightly different, and I have to return back essentially the same random number in encrypted form. Okay. Okay, so that's these are things you might not have really thought about if you just trusted that encryption was enough. That should show that it isn't. Okay, so just one more minute. Sorry, I'm a couple minutes late here. So the takeaways here are that secure communication involves many considerations. Just having encryption primitives is not enough. They have to be used carefully, right? You have to avoid all these clever attacks like replay attacks. And authentication is still not a fully solved problem because the PKI, public key infrastructure, has many drawbacks. Like the certificate revocation lists have to be checked at some frequency that is like a trade-off between accuracy and scalability. So as a network or software engineer, I have a few key lessons here. So first, mainly it's like just use the latest version of TLS. Don't try to re-implement it yourself. And use the latest version because as new exploits are discovered, and they're more subtle than just these simple replay attacks, but things like that, those get solved in fixed in later versions. Don't try to build your own encryption scheme from scratch, and understand how the public key infrastructure and certificates work, because in order to use TLS, you generally have to generate certificates and put them in the right places, and have them generated correctly, and of course keep their private keys safe. Okay. So yeah, this is another recap, I guess. We talked about public key infrastructure to convey transit trust, cryptographic hash functions prevent you from signing. Ensure that when you sign a document, you're not signing other documents that can be used against you, and are also using MACs. And TLS is an implementation of all this stuff inside of a TCP stream. Okay, so see you next time.